Hi there, and thanks for joining us for this session on how next generation science standards really work, setting up for claim, evidence, and reasoning, really going beyond just the CER model. My name is Francis Vigent. I am a former teacher myself. I taught high school math as well as elementary and middle school science, technology, and math for about 10 years. And with all the changes that are happening to the next generation science standards, I think this particular webinar speaks to kind of pulling a lot of the pieces together. We have standards. There are a lot of different products out there right now that are saying that they're 100% NGSS aligned, and this webinar kind of talks a bit about what alignment means in the sense of what we think of in terms of student learning outcomes, and particularly this claim, evidence, reasoning model that's making a leap from the ELA world into the science world. Claim, evidence, and reasoning has always been a part of science and engineering, but it actually goes beyond that, and that's of course where we get the title of our webinar today. So just a quick bit about KnowAtom. KnowAtom is located just north of Boston in Salem, Massachusetts. We are an organization of educators who are really focused on critical thinking skills, specifically developing students' ability to create, evaluate, and analyze. We also happen to really love science, technology, engineering, and math, or the acronym that most folks refer to as STEM these days, or STEAM when we involve the arts. And the connection here is really that we believe STEM, or science and engineering, is the best environment to teach children critical thinking skills. And not to say that the arts are not. In fact, the other really great discipline for teaching these critical thinking skills is English language arts. And we'll see how that connects here as well with the claim, evidence, reasoning model. So of course, that relates to professional development materials, curriculum, and things like that. So throughout this webinar, what we're going to do is, if you're on the live session, on the side of your screen you will see an area where you can submit questions. I'll do my best to keep an eye on those questions throughout the webinar. If you are not on the live session, please feel free to reach out to us by email or go to our website, KnowAtom.com. Click at the top of the screen, I believe under About, or you'll see Contact Us, and also on the footer. Feel free to reach out. I'll also give you my contact information at the end of the webinar and some other folks here. So without further ado, let's jump in. We're going to try to take about an hour, and I'm going to try and save about 15 minutes to answer questions that I have not been able to answer during the webinar. If you think that perhaps I answered your question or maybe misinterpreted your question, feel free to ask it again. So here we go. So the first bit of what we want to talk about when we talk about how the next generation science standards really work is how to differentiate between science and engineering, particularly as it relates to next generation science standards. So for the longest time, if you were to walk into a science classroom, students would have science books in front of them, and they would be learning about the facts of what a rock is, what a mineral is, the difference between sedimentary and igneous rock. They would be learning that rocks are formed in the rock cycle. You would be in a biology class and you'd be learning about ATP, what ATP stands for, adenosine triphosphate. You'd be learning about chemical and molecular bonds and covalent bonds and these sort of things. So very focused on the facts. And people would often look at an engineering class and say, oh, that's where they build things. So, tech workshop is where we cut wood and we build, birdhouses and things like this. And I'm not giving these examples to make a mockery at all, and I hope that that's not misinterpreted. But that is and was my experience, that in tech engineering class we, cut wood and we made birdhouses and we made, little paddle boats that would float on water. And so that may or may not fit with your idea of what science and engineering or engineering is. But under the next generation science standards, we have a very specific picture and idea and in fact definition of what science and engineering is. scientists don't set out to learn all the facts of what other scientists have done. They don't try and internalize encyclopedic knowledge. They don't try to bring that encyclopedia inside them. What scientists do is that scientists ask questions and they answer those questions by planning experiments and carrying out those experiments to gather data and to reflect on the hypothetical answer to that question that they are testing. Okay, so that's how scientists go from a question to develop an experiment, or even before that, to come to a general sense of what they think may be an answer to that question, and then they develop a plan for how they're going to test what they think. That's the experiment. They carry that out, they get data, and that data allows them to analyze and evaluate what they think is the answer to that question. And that's where conclusions come in, evidence-based conclusions, and that's where claim, evidence, and reasoning models fit. It's really at the very end of a scientific process. Okay, so scientists give us new knowledge, or scientific knowledge, knowledge from experimentation. Engineers don't necessarily build anything. And building is a strange kind of word in a sense that construction workers build things, but they don't engineer anything. So if you think about that, how is it that if you use the definition, and this is the problem with the definition, the idea that engineers build things. One, engineers don't always make things that are physical. They can be non-physical. Computer programs are engineered. You can't touch a computer program. Processes in factories to ensure quality control, to prevent cross-contamination, are engineered, but you can't touch a process. Right? It's intellectual in its very nature, just the way that a computer program is sort of intellectual in nature. It's not tangible. So engineers are not, so if you, let's back up a second here. So if you think about it in the classroom, if we use the definition of engineering as building something, well, it can be non-physical, so that's a problem. But let's go beyond that. Construction workers build things, but they're not engineers. Well, construction workers follow the design of somebody else. Now, engineers might be involved in that design. They are involved in that design if the design solves a problem. And typically, you can imagine anytime you build a building, typically you have to overcome problems, which is why we have civil engineers that often get involved in building design. And then creating those plans that the construction workers follow. So followers are not engineers. Okay? Engineers are creators. The same thing with scientists. Scientists are not followers. Scientists are creators. And so from a curriculum standpoint, I guess just a little, what does this mean for the classroom from a curriculum perspective? I want to point this out right away, is that anything that children are following in terms of, picture diagrams, make by number, all of that sort of thing, you can see how that's got an alignment issue right from the get-go. Okay. Writing up a plan on the board, having children copy it, and then carry that out, that's a problem because students are not actually engaging as scientists or engineers in that situation. So keep that in mind. So back to this, how to actually differentiate between science and engineering. Well, we said that scientists ask questions, and they develop hypotheses, they test those hypotheses, gather data, and then they reflect back. Engineers use their scientific knowledge to solve problems that they identify. So engineers identify problems, they use their scientific knowledge to try and solve those problems, and they do it by developing prototypes and testing prototypes. So civil engineers, there's kind of a little bit of a joke in the engineering world. They're kind of, amongst engineers, if you meet a group of engineers from all different disciplines, the aeronautical engineers are probably going to think of themselves as a little bit above electrical engineers, and electrical engineers are going to think of themselves as a little bit above civil engineers. And it's just kind of this sort of historical kind of hierarchy that sort of happens informally within engineering as folks kind of, you know, joke and jest with each other. Civil engineers are oftentimes, you know, working with tables and formulas and things like that that are already known. So they're not necessarily going through a prototyping process the way that somebody who was really kind of the first civil engineer that really solved the problem of deciding how to design a beam and what loads it would be able to carry and so on, actually prototyped that I-beam and that material and carried out the testing from a prototype standpoint, and then, you know, published that data and scaled up the solution as, you know, a steel I-beam that anyone could use in a structure. So think of engineers or engineering itself as being a process of identifying problems and then solving problems by looking at the available resources, developing or considering different approaches to the issue, and then developing a targeted prototype which is tested and yields data which the engineers can use to reflect back on whether or not that prototype actually solves the problem. Because that is the actual process that gives us technology. So that's kind of, you think of it as innovation. So engineers produce technology. And so when you think about what's on your screen right now, this entire STEM cycle is also a cycle of innovation. Okay, that technology enables scientists, you know, sort of to become aware of new questions, to be able to answer questions that they haven't been able to answer before, that they may have. And a good example of that is outer space. We have questions about outer space that we just can't answer because we don't have the technology yet. But when engineers use their knowledge of science, perhaps electronics and materials and how to do analog to digital conversion over great distances with low energy, that technology becomes available in the form of space probes, because engineers are able to design those, and those space probes then enable scientists to answer those questions and so on. So engineers and scientists have very different roles, but they're interrelated and they're connected. They engage in different processes as well, although they will use all the same science and engineering practices. I just want to mention math here because we've talked about science, engineering, and technology. Technology solves a problem for humans or for animals or so on, you know, created by people. Math is at the center of it all because math is the tool for quantifying, analyzing, communicating, and evaluating observations. So when you think about talking about something that's blue, well, blue to you is subjective, blue to me is subjective. We might have a range of ideas of what we think of as blue. But in the case of science, or in the case of engineering, we can talk about a specific wavelength. We can actually quantify that thanks to, you know, 5,000 nanometers or something like this. We can actually communicate a wavelength using math. And math comes into play in not just in the observations, but the analysis, so finding mean, median, mode, differences of averages, and then, of course, more advanced statistics like standard deviation, standard error, and things like this, which we wouldn't necessarily get into at the lower levels, but just to kind of give you an orientation point here. Oftentimes in NGSS, the nature of science and engineering, which is what I'm describing and showing to you here, is exactly called that. It's called the nature of science and engineering, and it's referred to oftentimes as the fourth dimension of the standards. So I'm sorry to take so much time on this at the start, but I want to just really lay that out there, because once we get into this claim evidence reasoning model, it's important for you to be able to think back to where it has a place in terms of science and engineering, because claim evidence and reasoning comes in at the very end in terms of the conclusions that scientists come to, and the conclusions that engineers come to in terms of the work that they have carried out. And so a bit of foreshadowing here is that in order to have claim evidence and reasoning, you have to have carried out some specific work as a scientist or as an engineer. So you're really starting at the point of a question or at the point of a problem that's been identified, okay? Another key point here is the science and engineering practices. There are 8 of them. These come directly again from NGSS, and this and the reason I'm bringing this up in connection with that nature of science engineering cycle that I just showed you is that some people think that science is about the natural world, and that engineering, again, is about building things. Well, again, it's not. Science and engineering is not a noun. It's actually more of a verb or even an adjective. Okay? Scientists and engineers do not do science. They do not do engineering. Okay? To do something is a rote process. Scientists are engaged in science, and engineers are engaged in being engineers. They are problem solving. They are solving problems. So there's a difference between being and doing. So to be a problem solver or to be someone who is asking questions and answering questions through experimentation, that's what it means to be a scientist or an engineer. So when you think about those 8 science and engineering practices I have on your screen right now, these are the skills that are specific to science and engineering, which students, and I want to underscore that it's the students that need to internalize these skills. Okay, so a student needs to be able to ask questions as a scientist would in a scientific context, and needs to be able to define problems as an engineer would in an engineering context. They need to not only be able to use a model, but they need to be able to develop one. So the old food chain, food web is a good example. We can show a food chain or food web and ask students to use it, right? That's old school. Or we can take a picture of the environment and we can challenge students to actually develop the model. How is it that these plants, animals, these organisms are interrelated? And so then that pulls out the food chains and also the food webs because they're interrelated. Students need to not only carry out investigations, right? The old, copy it off the board, follow the number, and so on and so forth. And this, they need to be able to plan the investigation themselves. And these 8 practices, and this particular one in specific, is a huge point of misalignment for a lot of programs that call themselves 100% NGSS aligned. Is right here at number 3. Are the students actually planning that investigation going from the question to the conclusion? Or is it somehow a make by number, make by picture, copy off the board, spoon-fed model? And I think a lot of people get confused because they think that it's scaffolding. Spoon feeding is not scaffolding. Make by number is not scaffolding. Okay? Scaffolding is about release of responsibility, adjusting supports. Make by number does none of that. Okay, nobody needs to assemble. You don't need to go home and disassemble and reassemble your kitchen table 100 times to appreciate the fact that it's a table. If you think about solving the problem of needing some place to eat when you sit in your chair, that sort of deductive process, looking at the resources that are available, might actually help you plan and carry out the process of actually prototyping and designing a table. But that's very different. That's very different than making by number the way that you would from a box out of IKEA. Analyzing and interpreting data. The difference here from a student's perspective is, I'm given a bunch of numbers and asked what do they mean. That's interpreting data. Analyzing data is looking at a data table and actually taking that data and making sense of it. What does this data actually mean? Maybe I have to find the average and then take the difference of the average to get to some meaning which is useful to reflect on the hypothetical answer to this question. Okay. Using mathematics and computational thinking, constructing explanations from science, designing solutions for engineering. These are kind of related but a little bit different. Constructing explanations, that evidence-based conclusion that we're talking about. That's where claim evidence reasoning fits in. Designing a solution is engaging in the engineering design process. So there's a scientific process and an engineering design process. And there's some variation, if you were to compare different processes. These are These are frameworks, and there's, depending on where and who's applying them, there can be agreement or disagreement on different elements of them. I'll show you one a little bit later on that's appropriate to K-12 that we've used for years that works well. The point I want to just pause on here very quickly is that these are the practices, the skills specific to science and engineering to actually engage as scientists and engineers in solving problems or answering questions. The process, different word, process, is how scientists and engineers actually advance logically from that question to an evidence-based conclusion, or from that problem that's been identified to an evidence-based solution. Okay. To engage in process, whether you call it the scientific process, the scientific method, the engineering design process, the engineering method, universal design, there's a lot of kind of blingy terms that people like to throw out here. The bottom line is that process does not mean that science is linear. The scientific method does not indicate or mean that science is linear. Same thing with the engineering design process. Both science and engineering are non-linear. And we'll get to that in a little bit, but I just don't want you to kind of hear that and think, oh, this is old school, whatever. Actually, science and engineering are very non-linear. And I'm going to explain that in a little bit. So engaging an argument from evidence is where claim evidence reasoning fits, and how we take what we've obtained and evaluate it and communicate that information in terms of persuasive argument about our hypothetical answer to our question, or our hypothetical solution to the problem. Okay, so practices are something common to scientists and engineers. They're kind of a skill set that they use. But when you think about the classroom, these are skills that students need to have internalized. Okay, if a teacher says, well, I do that, well, it doesn't matter that you do it as a teacher. I can go and develop a model in front of my students, but that doesn't really mean anything, because can they actually, do they have the skill to be able to develop a model on their own in an unfamiliar context, extending and developing and using the knowledge that they have? And that's how these NGSS standards take the definition of science and engineering and go beyond the standards that we had previously in almost every state, really go beyond those standards we had previously by adding in the science and engineering practices dimension. So let's move away from this differentiating between science and engineering, and let's go to let's go over to claim evidence reasoning and connect this up. So let's see here. Just taking a quick look at some questions, make sure we're answering this. And as we're making this transition, a few of the questions that are out there have to do with how knowledge fits. So when we talk about this model of differentiating between science and engineering and the practices, doesn't knowledge have a purpose? And I would say yes, it does. Of course it does. Just the way that the metal or wood in the table that you build to solve the problem of someplace to eat when you're sitting in your chair at home for dinner solves or serves a purpose. Okay. The thing is that wood in and of itself does not solve that problem of a place to eat. Okay, it's the technology, it's the actual solution that develops and uses the wood and turns it into a table that that solves that problem. Okay, facts are important, and I will pull up this diagram really quick. It's far down in our presentation, but it fits here. When you think of higher order thinking, the role of higher order thinking, remembering, understanding, and applying is lower order thinking skills. That is, the typical knowledge of science, right? It's what we look backwards to what scientists have discovered, definitions of words, what engineers have created in terms of technology, right? If you can remember it, you can understand the basics, maybe you can apply it, great. Those are all lower order thinking skills. What the new standards require is creating, evaluating, and analyzing simultaneously to take that general knowledge and actually extend it into the unknown. Okay, and so it's not enough to just have knowledge. I'm not saying that knowledge isn't important, it's just insufficient. And you can imagine that the amount of knowledge society has generated to this point in science and in engineering is so extensive that any one human cannot possess all this knowledge on their own. The real value add of problem solving and answering questions at this point is the ability to extend knowledge further, and which is why the ability to create, evaluate, and analyze as scientists and engineers do using those practices is so vital, and why the NGSS have moved in that direction. And you know, so I hope that gives you a little bit of a picture. Some other folks have asked questions about different types of science, and also about the arts, and just to kind of throw that in there, we're gonna get to the arts more in a little bit. I'm going to come back to that that question. In terms of different types of science, you can tack anything in front of science here. You could put you know, life science, physical science, food science, electrical science, and so on and so forth. The bottom line, though, is it's only, and it's somebody, a friend of mine joked about this. He said, you know, anytime somebody puts the word science in front of something like computer science, it's probably not a science anymore. So if whatever you know, electrical science, for instance, if you are engaging in trying to create, evaluate, and analyze extending the knowledge of electricity, the electrical properties of materials, then you are engaged in electrical science. If you are taking the known properties of electricity and using it to solve problems, you are engaged in electrical engineering. If you are learning about what electrical scientists have discovered, you're actually learning about history. Okay, so that is kind of the unfortunate reality of the traditional nature of science and engineering in the classroom, is that we've really been teaching history of science and the history of engineering, and in the case of engineering, just kind of making things. Oftentimes we've been teaching kind of crafting, and so that's the difference between engineering and crafting, is that engineers solve problems, crafters just make things. And maybe, you know, who knows, we could extend that further and have more discussion about that. So you know, these are interesting questions that, you know, I want to address here, but it's key to understanding how this claim evidence reasoning comes together, because claim evidence reasoning comes at the end of a scientific investigation or an engineering design investigation. This is how claim evidence reasoning is commonly applied in an ELA context. Okay, people oftentimes, and I'm taking this from an actual Matthew Delisio, a teacher's rendition of claim evidence reasoning, because I want to show how it's really not applied properly. So when you think about claim evidence reasoning, oftentimes people think that claim is your answer to the question, it's what you think, that reasoning is the general principles about the way the world works that allow you to link the evidence to the claim, so it's what you know, and that evidence is actual observations or measurements that support the claim, but then they think of it as what you see. So the thing to point out here is really what is missing or implied by this claim evidence reasoning framework. Okay, so think about that. What is missing, what's implied by this framework? The first thing I want to point out is that when you think about just the claim itself, is the question, what are you making a claim about? Okay, so before you can make a claim, and this is especially true in the case of science or in engineering it would be a problem and not a question, is that you need to have identified a question. All right. The second thing that's implied here is that there is a hypothesis involved, and saying what you think is actually an improper way of forming a hypothesis. A hypothesis is the hypothetical answer to a scientific question. So it's not, you know, I predict or I think that X, Y, Z and fill in the blank, but in fact, if you know, the question is, and I'll use this a little bit later, if the question is, do plants require light to grow, a hypothetical answer to that question is that plants do not require light to grow. It's an actual statement that can be tested. It is either true or it is false. And people get into trouble here because they start to add qualifying pieces in here, like because. Because signals evidence. If you start to get into extended logic, like if then it's going to complicate and make your testing even more complex. So right from the get-go, there's a little bit that's missing here, that if you just think that having a student make a claim and have some evidence and reasoning involved, that it's enough in terms of forming an evidence-based conclusion in the context of science or engineering under NGSS, you're falling short. Okay. The next thing that's implied, or in a sense, is what I pointed out earlier. What's wrong with the definition of claim? Well, saying what you think is subjective. It's not objective. Okay, that's why I predict, I think, and hypotheses or claims that are formed that way are inaccurate. There's something that students will have to unlearn when they get to real science. So the question is do you want to do real science sooner or later, I guess. But in our case, we approach real science right away. We don't teach students the I predict, I think way of doing things, because they're going to have to unlearn that, or they're going to struggle if they pursue science or engineering for real. So, and the difference between subjective and objective. Subjective, what you think is, your opinion, it's what's in your mind, whatever. Objective is something that is either true or it is false. Okay? Scientists focus on objective claims because, and engineers as well, and that's because that what is objective is testable. It's something that can be proven through the use of an experiment. Okay? I want to ask a similar question of what's wrong with this definition of evidence. Okay? What you see. What you see implies qualitative support is okay. But the issue here is that scientists and engineers, so the word qualitative means, back to my earlier example, blue. Blue to you may not be blue to me. The quality of something being blue is open to interpretation. It's subjective, okay? Scientists and engineers want quantitative evidence. They want quantitative support, okay? That's why we would refer as scientists to light in terms of its wavelength, because the wavelength of 700 nanometers is a specific form of light that we can have no ambiguity about, okay? And so by taking something like blue and referring to it in its wavelength instead of as, or a specific wavelength of blue, you and I will know exactly what we're talking about, okay? So it's not what you see, because seeing something is not a measurement, okay? It's what you can measure. And we, in education, this is one of the places where I think we can take some issue with science at times, because we know through standardized testing that the qualitative things, the things that are hard to measure of our students, aren't measured oftentimes by standardized testing. Why is that? Because those, grit, for instance, is very hard to quantify. It's very hard to measure. And so, if we can take something like grit, which we might agree on qualitatively, and we could actually quantify that, if we could actually measure that, then that might be something that could improve standardized testing instead of just focusing on facts. And that's why if you're from DC or Illinois or another state that has NGSS testing already in place and operational, or if you're from any state that used PARC or Smart or Balanced assessments this year in ELA, performance-based testing is starting to blend qualitative and quantitative, and that's again where claim evidence reasoning model starts to fit in a little bit. So I'm going to continue on here. So the key takeaway is that evidence is not just an observation. It's a specific type of observation, and actually evidence is the result of analyzing observations, specifically quantitative observations. Okay? So I want to ask the question, why are we making a claim anyhow? So if you think about a scientist or an engineer making a claim, and when I say we, I'm saying as a student in your classroom who's in the role of scientist or in the role of engineer, because that's how we're learning science and engineering now, whether we're in first grade, fifth grade, 8th grade, 12th grade. If you're using a claim evidence reasoning model, students better be engaged as scientists or engineers, or you're losing out on a lot of value, right? We don't want like the workbook with the questions that somebody stuck in there and kind of set it on autopilot, or again, students copying off the board or being given a handout that they follow, or a picture, diagram, how to make something, or being shown how something's done and then being sent back to go do it on their own. Okay, we want students actually engaging authentically. So let's assume students have done that. They've gone through, they have asked a question, they've formed a hypothesis, they've planned an experiment, carried that out, gathered data, and analyzed it, and now they're at the point of forming a conclusion. We have to ask ourselves, as scientists or engineers, why are we making a claim? Well, as scientists, we're trying to answer the question with evidence from our experiment. Okay, so the question's big, right? Our experiment was looking at a specific answer to this question, whether or not it's true or false, or supported or not supported through experimentation. So that's where the hypothesis comes in, because the hypothesis is what we're making a claim about. Okay, so why we're making a claim is because we have a question. What we're making a claim about is the hypothetical answer to the question. It's the hypothesis is what we've tested. It's why we're gathering data as scientists, or why we're gathering data as engineers. Now, in the case of engineering, instead of a hypothesis, we would have a prototype solution, okay, because they use a different process, because they serve a different purpose. But I'm trying to focus on science here so that you don't get too confused between multiple processes, okay? So how are we making a logical argument? If we take this person's rendition of claim evidence reasoning, is it actually logical when we look at the way that this is framed? Does it, should you go from a claim to reasoning and then give evidence? And I hope you're saying no. Unfortunately, this person and some documentation, depending on which documentation you look to, will talk about reasoning as linking, and you see right here, linking the evidence to the claim. It's actually a little different than that, okay? Structurally, a scientific claim is supported by what evidence is found, and the reasoning explains how the evidence justifies the claim and answers the question, okay? So it's actually flipped. And so in ELA, you can get away with this. And the reason that you can get away with, this person's rendition of claim reasoning evidence instead of claim evidence reasoning is that the claim is subjective. In ELA, oftentimes claims are subjective. Was Tom Sawyer truly innocent? As a character, in the book, or was Jim truly free? Could Jim ever be truly free? Those are questions which have claims that are entirely subjective, and so by putting reasoning between evidence and the claim, you can kind of get away with it. By trying to, proof text is what you might call this. basically find some reasoning and evidence to, generate reasoning and find evidence to support it. It's called that proof texting. It's really kind of a sloppy way of doing things, but you can get away with it. In the case of science and engineering, you can't. It really should be the other way around, because just as I said here, you make a claim about your hypothesis, is it supported or not supported, as an answer to the question, and then you actually reason that support and justify how that claim is legitimate and whether or not the hypothesis answers the question. So it really, in a scientific context, should look like this. It should be claim, evidence, reasoning, with the reasoning going back and taking the evidence and using it as support for the claim. Okay. Now the thing is, back to what we initially talked about, you can't start a conclusion with a claim. You actually have to start at the question and hypothesis. Now, you can get away with just the hypothesis, but a really well-formed conclusion goes all the way back to the question. Okay, so I'm going to give you an example of what this looks like and how it works. Okay, so how to make a claim in the context of science or engineering. In the case of engineering, just think about hypothesis is in fact not a hypothesis, it's a prototype solution. This is an example of what, and when I pop this up on your screen, don't freak out. This is what claim, evidence, reasoning would look like in the form of a conclusion to the scientific process in a 5th grade science class. Okay. Now you may look at this and say, my 5th graders, they can't do this, they don't do this, and I'm sorry if you feel that way. 5th graders can do this. They regularly do this. But they only can do this if they understand the framework and if they have been taught in an environment that's going to develop the skills for them to be able to perform at a mastery level. And that's what we're talking about here today, is mastery level readiness. Okay, so I'm going to walk you through this, and then I'm going to show you how the question, the hypothesis, claim, evidence, reasoning all come together. So picture this as the conclusion to an experiment that I as a student did in your classroom. So in this experiment, we attempted to answer the question, can plants grow without exposure to light? By testing the hypothesis that plants need light to grow. We experimented by comparing the growth of corn seeds planted in an environment that is always lit to the growth of seeds planted in complete darkness. The result of our experiment did not support this hypothesis. Over 5 trials, we found that corn seeds planted in total darkness will still sprout and grow. On average, seeds planted in total darkness grew to 3 centimeters and died 5 days later, almost entirely white in color. Seeds planted in a totally lit environment grew an average of 90.4 centimeters taller and died 15 days later, with leaves turning from green to yellow. While our hypothesis was false, corn can grow a little in unlit environments. The presence of light helped the lit test group, oh, look, there's a typo, in the lit test group grow 90.4 centimeters taller and live 10 days longer on average. We believe that plants may have adapted to grow for a short time in the darkness of soil underground, and that light and dark cycles may be necessary for plants to reach their full maturity. These hypotheses would require additional testing. So, obviously a student who is performing, well at grade level, a student who has, solid ELA skills here as well. But let's look at how this plays out. So what I have done here is I've highlighted these different parts, the question, the hypothesis, the claim, the evidence, and the reasoning in different colors. And what I have grayed out is kind of quasi-reasoning. It's more just ELA, good ELA skills, okay? So I want to unpack this here. And back to that talk about does knowledge matter? Of course knowledge matters, right? In order to talk about growth or to talk about the average of something, I actually need to know what growth and average mean as words. I need to be able to use them. But you can see how I am using them to form a persuasive argument here. Back to the science and engineering practices we talked about earlier. Forming an argument from evidence is exactly what's going on here. Okay, so the question, what's the question? It's, can plants grow without exposure to light? What's the hypothesis? The hypothesis is that plants need light to grow. What is the claim that's being made? It's that the results of our experiment did not support this hypothesis. And what evidence did we give? We didn't give all of the observations from our data table. I didn't show you a data table, but we didn't use even a single observation directly from our data table in terms of raw data. What did we do? We talked about over 5 trials that the corn seeds planted in total darkness were able to sprout and grow. So in and of itself, because of the simplicity of this hypothesis, in and of itself, that invalidates our hypothesis. It does not, our hypothesis is not supported. But I'm giving key evidence here, and this is what I mean by key evidence. On average, the seeds planted in total darkness grew 3 centimeters, and I would push the student even further to say grew 3 centimeters in total, or only 3 centimeters, and died 5 days later. Why is died 5 days later not highlighted as evidence? Well, it's not really relevant to the hypothesis, right? Whether or not they grow 5 days later doesn't really matter. The fact that they only grew 3 centimeters, or that they grew 3 centimeters at all, is sufficient evidence to, and disprove is a strong statement, but in essence, disprove the hypothesis here, okay? But let's take a look at the reasoning, because the 5 days later is actually helpful in some reasoning, and could actually help the student build the claim evidence reasoning further, or build up this conclusion further, okay? So the reasoning here is that the seeds planted in a totally lit environment grew and so this comparison that happens, seeds planted in a totally lit environment grew an average of 90 centimeters taller and died 15 days later with leaves turning from green to yellow. So it's like a little bit of additional evidence support, but it's going to support our reasoning. While our hypothesis was false, why? Because corn can grow a little in unlit environments, or just can grow, period, in unlit environments. The presence of light helped the lit test group grow 90.4 centimeters taller and live 10 days longer on average. So what we're doing here is we're actually saying that there may be something else at play. We're reasoning not only that, the data is here to support the hypothesis because, well, it only was 3 centimeters, but we're actually beginning to pivot. And this is where people really misunderstand the scientific and engineering design processes, is that science and engineering are nonlinear because as we form conclusions, we begin to pivot. We take what we learned and we begin to pivot, and this is where it's happening right here, okay? Essentially, we believe that plants may have adapted to grow for a short time in the darkness of soil underground, and that light and dark cycles may be necessary for plants to reach their full maturity. These hypotheses would require additional testing. How is that setting us up in terms of reasoning for a pivot here? Well, when you look at the data that was presented, and how is this a persuasive writing piece as well, we're saying that yes, we were disproved. However, light had an effect, and it actually had a positive effect because the amount that the plant was able to grow was significantly more. Okay, that's one. 2, what we're also saying is that the plant was able to live longer and that its characteristics in terms of its actual physical qualities were different. One was entirely white and the other was, this green-yellow. We're going to extend, this is the pivot, that perhaps the plants died because they actually need both light and dark in order to reach full maturity. And the reason that we may have had any growth at all in this group that we didn't expect growth is because those seeds are living underground. They start off underground and need to be able to sprout without light present within soil. And so we would need some additional testing, to test these different hypotheses we're talking about. But in fact, that's what seeds do, right? A seed has a little bit of energy stored with it in those carbohydrates, and so the seed sprouts in darkness, and its job is to send a root and a shoot so that the root can gather nutrients and water, and the shoot can gather sunlight, and it can begin to engage in photosynthesis, and that is where the matter and the actual plant growth and development comes from. So this is not inaccurate. It's actually thinking, it's that creating, evaluating, and analyzing those higher order thinking skills coming to life. But bringing it back to the purpose of our discussion here is that we are using all of those science and engineering practices. We are using the scientific, this is the result of the scientific process, having engaged in actually asking a question, a little bit of research, taking what we know, developing a hypothesis, and then a plan to test that hypothesis using the data that resulted in order to reflect on the hypothesis, and this is what you get at the very end, okay? Which is going to then spawn, like we go back to that nature of science and engineering, the STEM cycle I talked about earlier. That's where you get new questions, new hypotheses, new tests, and where this all becomes very nonlinear very quickly, okay? So, I want to point that out. And again, this is a 5th grade level. This is not perfect by any means. You can see just as we read through it that things, just like ELA. And this is also where the disciplines integrate and where next generation science standards are by design naturally integrated, but where you can see those evidence-based writing skills, process writing skills, and all of that coming to life, not only in the conclusion, but in the processes themselves, okay? So what I'd like to talk about now is a bit of how and why we introduce processes and how that fits with this. So there are a few questions out there about this, and I'm going to try to get to that. Please ask your question again later if I haven't answered it. Okay. Now let's see here. Let's jump ahead. So another way to think about a conclusion is really aligning what we have engaged in as scientists or as engineers with the purpose of being a scientist or engineer, okay? So if you think about it this way, as a scientist or engineer, you had this, so it's a scientist, I'm just gonna stick with one, okay? If you have questions about engineering, please ask them. I just don't want to confuse anybody. So as a scientist, you ask a question, all right? That question is why you are engaging in anything, is to try and find an answer, okay? So the question yields a hypothetical answer that you're going to test. So the next piece, so you go from why to what. So what we did with that question and that idea that we had that may be an answer to the question is that we planned an experiment, okay? We planned an experiment, and that's where we use the scientific or engineering design process, okay? That process is going to require us to use all of those 8 practices from NGSS, the science and engineering practices, the skills specific to the discipline. We're going to have to develop models. We're going to have to ask a question. We're going to have to gather evidence. We're going to have to not only obtain it, but evaluate it, analyze it. We're going to have to argue from that analysis, and so on and so forth. That's what we're going to have to do, okay, as part of that process. And in fact, the scientific process starts with a question. The engineering design process starts by identifying a problem. So a proper process actually is integrated, and I'll show you what that looks like in a moment. So the next bit is how we understand the question or the hypothesis as a result of engaging and carrying out our plan, whether it's scientific or engineering, okay? And that's where the claim, evidence, reasoning comes in. Remember, if we look back here, you see claim, you see evidence, you see reasoning, but the question and hypothesis is what frames the whole thing. And the little bit of ELA that I've skills that I've grayed out up here, in this experiment we attempted to answer so on and so forth by testing the hypothesis. We experimented by comparing the growth of corn seeds planted in an environment, so on. That is good persuasive writing skills. Okay, that's just basic ELA skills. I'm not saying that your students are top-notch with their ELA skills, but you can see how having ELA skills, whether it's verbal, you have English language learners and they're going to verbalize this because they're verbal first, fine, no problem. Okay, because language is just a reflection of thinking, and that's what's key here. Okay, and the thinking and the purpose and all of this emanates from the question and the hypothesis, and that gives purpose to our claim and to our evidence, to our reasoning. So if we go back over here, okay, why we did it and what we did, what we did has purpose because of why we were doing it. And how we now understand the question and the hypothesis better is as a result of what we did. And the reason we did that was to be able to understand the hypothesis better. And the reason we wanted to understand the hypothesis better is because we were trying to answer a question that we had asked. Okay? And one of the places people go off the rails right away with all of this is that the students aren't actually asking a question. Okay? It doesn't mean that there's an art form to getting a question out in front of students, a target question, but you have to try to artfully draw it from the students, whether it's a group or individually, and typically it's as a group at the K-12 level. Okay, I am going to run a bit over time here, just looking at things, so I just want to let you know I'm still going to save time for questions, but this is probably going to run at least another 15 to 20 minutes, so I'm going to warn you here. We will send a link. I'll have Mary Ellen send a link to you. You can go on our website, by the way, and if you want to see curriculum that sets classrooms up for this, you can go on our website and download that, knowatom.com/curriculum, or you can just go to knowatom.com, look at STEM curriculum, scroll down, pick a grade level. I'm not hawking curriculum. We do have curriculum and materials and professional development available for purchase. So if you don't want to go through trying to set this up in your curriculum for each grade level entire year long, making it scalable, having all the materials to fit that and everything else, or if you're thinking from a district perspective, how do you help everybody be on the same page, support veteran teachers as well as newcomers and everybody in between. That's why we exist, is to make this something that is scalable and doable in the available time on learning at not just an individual level in the classroom, but also at school and district level. So feel free to reach out about that. You can go to our website. There's a contact us. You can just go to the top nav and check it out. So on and so forth. But I'm going to continue on here. And we'll send out a link to the video recording. Keep an eye on your junk mail, spam filter, all of that sort of stuff. There'll be a follow-up with that. If you don't get it, feel free to reach back through contact us and reference this webinar. So anyway, continuing on my way. So how we understand the question or hypothesis is as a result of engaging in that planned investigation, the experiment, and analyzing the data and reflecting on the hypothesis. Okay, that experiment changes how we think. That's why the scientific process, that's why the engineering design process is not only relevant, it is super relevant. And anybody who's not engaging in it is engaging only in isolated practices and sort of coaching students through the motions of science or engineering. And it's not, I'm not vilifying anybody who's doing that, because a lot of people don't know any better. It's how teachers are taught to teach science. And in fact, people who are engaged in any practices or processes at all are on the top side of things, because there are a lot of folks who don't engage in any practices or processes at all. And I don't mean themselves as teachers, but engage the students in those, actually challenge them to engage in the practices and processes. So you can see, the old textbook model does not fit here. And the reason is that if we slide over, and the reason you see this off to the side is that our conclusion is really how we now understand the question or hypothesis using that claim evidence reasoning model with the question, with the hypothesis in place, and is going to look back and support, basically answer the question, does our analysis reflect how does our analysis reflect on our plan, and how does our results impact the question or hypothesis? Okay, it's that culminating sort of reflection point. All of this does not fit well in a traditional model of instruction. This is what I was just describing to you. That idea that content flows through a teacher, the teacher models it, explains it, and demonstrates it, and the student just absorbs it and has to recall, repeat, or summarize those facts. That's the old rote recall model, and that's what standardized testing has traditionally been geared around. And that's why you see performance-based assessment being taking center stage and taking over all of those multiple choice, fill-in-the-blank type, lower order thinking questions that have been out there, because computers can do those tests all on their own, just using basic logic and search algorithms. What humans can do that's really unique is to go beyond that. Okay, and so so don't banish students to a repeat, recall, and summarize definition of proficiency. Okay, instead take on a next generation model of instruction where the role of the teacher is to play the coach, to gradually adjust the student supports, to help students understand how to engage appropriately, and to redirect and monitor them as that full release of responsibility occurs over that first 10 weeks of school. And then the challenge builds further and further and further. And by challenge, I don't mean a specific task. By challenge, I mean the depth of thinking, the depth of creativity, the depth of analysis and evaluation is pushed further and further. And that's why you see the teacher not getting between the student and the content, but in fact being to the side and strengthening the connection between the two. And these terms are very deliberate terms that we've chosen here. It's that the students are developing the science and engineering practices, those skills specific to being a scientist or engineer, actually engaging in developing and using the content, which is those disciplinary core ideas, and being able to observe and connect that content across the disciplines through use of the cross-cutting concepts, which is something that they will observe and also be able to identify. Okay, so the expectations of a student are very, very different in this environment. The expectations of a student are that they will be able to develop and use the content with these skills. And so being able to use the skills to solve problems and answer questions, because that's how, and that's key here. Some folks have asked how to introduce practices and processes. You know how you do it? It's really simple. Solve problems and answer questions. And don't you do it as a teacher. Make the students do it. And I don't mean make in a forceful sense, but I mean make in a challenge. Challenge the students to solve problems and answer questions. When people look at our curriculum, they misinterpret sometimes, looking at it as, oh my goodness, you know, like they either will look at it as something a student maybe couldn't do in some cases because, you know, nobody has done it for them. How am I going to do this for all the students? So they might be alarmed there. In the other case, they might look at it and say, this is scripted. The reality is that it's not scripted. In our curriculum, what we do is you know, if you look at a curriculum piece, we are supporting a teacher to be able to understand the boundaries, or at least a mean expectation of a student, and how to scaffold and release that responsibility over time. So we're giving teachers guidance so that they can deliver effective science and engineering instruction in the classroom. And they can do it hands-on in a problem-based sense, in a problem-based manner, every lesson of the year. Okay, all year long and from one grade level to the next, so that students are constantly being intentionally nurtured one grade to the next, and from September through June or August through July, depending on where you're coming from. So, you know, so that is, you know, setting students up for that challenge and supporting teachers takes a lot of effort, a lot of thought, and a lot of, you know, testing and design and all of that. So I don't know, you know, and I'll criticize Massachusetts as an example. It's where I grew up. You know, Massachusetts has turned around, and by adopting, they have adopted the next generation science standards. They tweaked it a little bit. It's considered an adaptation. And then they got a bunch of people together, curriculum leaders and everybody else, and they said that, you know, they think that teachers should be developing their own curriculum for these. And I just don't know how, as a teacher myself, I just don't know how that is a realistic or fair expectation of a teacher. on many levels, time-wise, resource-wise, funding, for materials that are necessary, and how it makes any sense from a system standpoint. Because I would criticize it to the point of saying that I believe it's actually setting districts up to fail. And I'll explain exactly what I mean by that. It sets districts up to fail because when you have everybody freelancing, out on their own, trying to find something from the internet, trying to find something that's claiming to be NGSS aligned, and trying to take something that they used to have and retool it into something that works. That takes multiple years because you have to create something, use it, see the result of it, and then take that information and iterate. So hopefully you get close. And if you don't, it's going to take another year and another year and another year. So that's one piece. Two, in order to do that for oneself, it takes an awful lot of time. That's what most people are doing, in the summer, every summer. But to do that in such a way that it's curriculum that outlives any particular one teacher, so that it's sustainable, and so that a child is intentionally nurtured from one grade level to the next, so that third grade fits with fourth grade and so on. And so that a new teacher coming into the district is right on the same page with everybody at the same time, is not something any one teacher should be charged with doing, because it's an unfair expectation. Nobody has the time for that. So I feel really bad for the folks who, rightfully so, go to the meetings, they listen to the folks at the state in Massachusetts, and they hear that, we have a bunch of time to just sort of try to create some things on our own, and just kind of roll with it, and that's actually going to result in something that's beneficial. And I think the thing that really bothers me most about it, and I don't mean to riff on this too much, is that the districts that are most likely to take that advice are the districts who really need the success the most. And I'll just leave it at that. And the place where people are trying really, really hard, perhaps without a lot of support, perhaps without a lot of resources, who could really benefit from support and from resources that would connect them with their peers, and you see in those environments oftentimes the most needy students. So I would say keep that in mind. So looking at this next generation model, in order to expect a student to be able to develop and use content to use the skills to answer questions and solve problems, and to be able to use the system behavior to describe dynamic interactions, this is not something, the skills are used over and over again. It's just like English language. I use words over and over again all day long, but I'm saying different things. Okay? So we're going to use the skills over and over again. The different things are the different experiences. So students are going to experience different content, different concepts all year long, and it's going to be scaffolded in such a way, at least this is the way it should be done, this is the way we do it, should be done this way, should be scaffolded in such a way that those concepts, one enhances the next. A lot of people try to start with engineering as a cheap way to hook people, hook the students. Hey, let's build something. Isn't science cool? Now don't you want to behave in science class and listen to everything I have to say to you? I don't know. Does that sound good to you? But that's what people try to do. Instead, what we want to do is we want to put students into contact with the content, challenge them to use the skills, and help them discover the knowledge themselves. And this is, it's an art. Again, it's tough to put, when I hear states saying, hey, teachers, just go and make all your own curriculum. I don't know, that's unfair to me. How you do that is very nuanced. But the thing I want you to take away from this is that learning that a student, as they uncover something, what they uncover, if they can then use that in their next investigation to answer a question, to solve a problem, using their ideas and their plans with the available materials, suddenly what they just learned has relevance and purpose, and what they're going to learn has relevance and purpose. It goes both ways. And then you go to the next lesson, and the next lesson, the next lesson, the next unit, and so on and so forth. And so that's how you truly scaffold, how you truly bring the practices and the processes together and bring students to mastery. And in order to get students into this level of thinking, and performance, because this definition of mastery is not, I wouldn't say it's, it has not hit a critical mass in the United States. These definitions of mastery have not hit a critical mass in the United States, and the bottom line is that until they do, students are going to need to be introduced to the expectations. So that's going to be up to teachers, again, as the coach, to help children understand the expectations of them as scientists and engineers in the classroom. And then furthermore, for teachers to step into the role of coach, the way that we're showing it here, and not as the role of expert and sage, because, everybody expects an adult to know more than an 8th grade or a 12th grade student, right? Because the adult, by virtue of having a job as a teacher, graduated from 12th grade, so they ought to know 12th grade science, right? Especially if they have a grade-specific licensure in science. They had to take science classes and pass a test. Nobody's doubting this. So this traditional model really serves very little purpose for student value and learning outcomes. So we have the new definition of effective STEM instruction from the National Research Council, and I'm just going to read this quickly. It's a shift from what you see on the left to what you see on the right. And so when you think about this claim evidence reasoning model, when you hear it, it's not enough, right? That's a little piece that needs to be augmented. That's a little piece that's coming from ELA that needs to be augmented and used within forming conclusions, but to get to that point starts much earlier, and this is where it starts. Effective STEM instruction starts by capitalizing on students' early interests and experiences, right? Pre-K, kindergarten, following and nurturing that student all the way up. Identifying and building on what they know, so it's that thoughtful, intentional unit, lesson, scaffolding within the year and also from year to year, right? Doing butterflies in spring because it's springtime and you can release them after you've just done electricity. Like what value does that add? It's nice to go outside and release butterflies, but you've lost so much value because electricity and butterflies don't really connect the way that they're typically done. Now, if you want to get into, sodium, potassium ion pumps and how butterflies actually move, be my guest. I guess, my hat's off to you and the connection there between electricity and life. But most people aren't taking that approach. Identifying and building on what students know. It's not only good enough to know what they've learned in the previous lesson or unit within the year, but it's really important that 2nd grade teachers are supporting 3rd grade supporting 4th grade, and vice versa. Because when you look not only at what students need to be college and career ready, to be able to perform well on AP tests, content-wise, but also in terms of knowledge and skills, new people come to the district. They need to join up. They need to know where they fit in the big picture of things. But from a student's perspective, it's really important that their experience is being taken into account, and that when they're tested in 4th grade or in 5th grade or in 8th grade and so on, those tests are covering not only 5th grade or 4th grade, but they're covering all the prior grades as well. So it's not just about a grade-specific standard occurring in a specific grade for mastery, right? And this is another point of misconception among folks. It's important that people understand that standards from prior grades are being reinforced all along the way, and that should be an intentional process, and that standards from future grade levels are being introduced within a particular grade level, and so on and so forth. So that's part of this, and identifying and building on what students know. It's much deeper. Providing students with experiences to engage them in the practices of science and sustain their interest is very deliberate wording. It's not ours. None of this is our wording, or my wording. It's the National Research Council's wording that forms the basis of, of these new standards. So experiences, that's what we've been talking about, students as scientists and engineers. Experiencing, really being challenged to engage in the practices, and the practices are those 8 science and engineering practices I started with. Okay, the kids you see on the left are just watching what somebody's doing, and they're going to go parrot it back and do it for themselves, just the way they saw it. Okay, the students on the right have done some nonfiction reading. They had a Socratic dialogue with their class, and now they are trying to solve a problem, extending what they know, using the skills they've developed. And you know what? They don't know how this is going to be solved. Nobody has given them a demonstration or shown them. That's up to them. And it either will or will not solve the problem. And it's their job as engineers to take their idea, whatever it is, bring it to life, gather the data, and reflect back on it. Okay? That doesn't mean that the teacher's not involved in checkpoints and helping to kind of monitor, redirect, and differentiate at points, but there's a full release responsibility here. Okay, and that's something that's been worked up to over the first 10 weeks of school, but it's a very different expectation, a very different type of performance from students, and that's why you see these new standards and being rendered as performance expectations and having 3 dimensions, right? This is the performance expectation, what a student is going to have to be able to perform as a result of classroom instruction, and it's going to require skills, which is the science and engineering practices dimension. It's going to require knowledge, which is that disciplinary core idea dimension, and it's going to require awareness and an ability to connect the discipline, different parts of these disciplinary core ideas, by virtue of the way that they behave as phenomena, and that's what cross-cutting concepts are about. Okay, so I want to transition over here quickly to not only connecting the practice with the process, but really how the evidence statements fit. Okay. And I have some examples of things I can show you too, but I'll skip that, skip over that for a little bit. So connecting standards to evidence statements. So what we just looked at is a standard, but it's really a performance expectation, even in an adaptive state. And I apologize again to people in Massachusetts. The other people I'll apologize to are the folks in West Virginia. Both of your states really did a number, particularly West Virginia did a number on the standards, trying to change them and so on. And the recommendations of how people should deal with this really, I don't think are helpful to educators in the field. But if you have further questions about that, please ask. So to go from what we see here as a performance expectation, what a student who has learned appropriately in the classroom, what they're going to be able to demonstrate in a new context, and a context that's not the result of direct instruction, means that the standards have to be translated into some kind of district curriculum, okay? And that district curriculum's job is to actually structure the student's experience. So that means supporting the educator with the background, unpacking the standards, giving them the lesson plans, what materials are required, actually supplying those materials, and the various assessments, vocabulary, concept assessments, reading checkpoints, and so on, to support that student's experience. Now, what I'm describing is not to say that the district should be taking away teacher creativity. What the district should be doing through the curriculum that it buys or that it develops or whatever, is that the curriculum should support a high quality, effective STEM experience for these students, to that definition I just described. It should be engaging students in the practices of science and engineering on an everyday basis. It should be intentionally nurturing them throughout the year and should be supporting that student's understanding and skill set from one year to the next, so that they are reaching mastery on purpose, with purpose, and not by accident or by chance, which is what results from this encouragement of, everybody, there's the frontier, every man for himself sort of encouragement that states will take basically as a result of not wanting, and the reason that they do it is because they don't want to fund the change. And I think that, if there's an elephant in the room, that's what it is. Because if somebody gets some success or pulls the funding from themselves or whatever in some way and things happen, then, improvement's improvement. So that student's experience is really what's going to produce the learning, right? Is the experience something that's going to challenge the student appropriately? Is it going to appropriately nurture them? And the way that we see that is not just qualitatively, but really through evidence of learning in terms of those evidence statements themselves. And this is the evidence, part of the evidence statements related to that earlier standard I was talking about. So the standard is, grade 5 standard, life science standard. Students should be able to develop a model to describe the movement of matter among plants, animals, decomposers, and the environment. So the first thing that probably comes to mind is food chains and food webs and so on and so forth. Now, if the experience involves reading about that from a textbook and that's it, and really it's not even necessary, but let's say that was it, then the student hasn't engaged in any of the practices, they haven't engaged in the processes, they haven't been challenged to actually solve a problem or answer a question the way that they're going to be challenged to demonstrate their understanding here. And so it's unlikely that they've learned what they need to from a skills perspective or even from a content perspective to be able to produce evidence. But here's how we can see. Here's what we should be able to see as evidence. We should be able to see that if we put a scenario in front of a student, let's say it's a picture of a forest or something like that with plants and animals and trees and all these sort of things that belong there, a student should be able to develop a model to describe that phenomenon that talks about the movement of matter within that picture as an ecosystem. Okay, specifically identifying what's relevant, that there are plants there, that there are animals there, that there are decomposers. What are the plants? What are the animals? What are the decomposers? What is matter? Okay, how are they connected? What is this environment? Is it is it a marine ecosystem? Is it a deciduous forest, or so on and so forth? How do those pieces form relationships? That's what you see here in 2. The student should be able to describe among those components what's relevant for describing the phenomenon. So the idea that matter is transferred and that energy flows from the sun to the producer, which is the plant, and then on to the consumer, which is the animal, and then on to other consumers, which are perhaps animals that eat animals, and so on. And so, and then so how does that matter energy get back into the environment, or should be recycled, particularly the matter? Well, decomposers, and who's playing that role? It's the fungi, the bacteria, and so on. So just in this sort of thought, sort of talking through this with you, you can see that these evidence statements are really spelling out not a task. See, that's the thing. This is not spelling out a task. It's spelling out the minimum characteristics of mastery. Okay, a student who has reached a mastery level is going to be able to fluidly pull the components, the relationships, and the connections together in this way, very fluidly, looking at an unfamiliar context, a scenario, and by virtue of somebody asking the student, prompting them in a series of questions that they might have on a standardized assessment, for instance, we should be able to tease out different aspects, any aspects we want that are described here in these evidence statements to show evidence that the student can perform the expectations of the standards. And so that's where you come back here. If you go from standard to evidence of learning, where you take something like these evidence statements and say, okay, today you need to know that animals consume plants, and also that animals consume other animals. And the animals are, the herbivores consume the plants, and the carnivores consume only animals. Okay, somebody who is very literal might say, look, that's how I'm going to go from the standard to evidence of learning. That's what's going to give us student learning. It doesn't work that way, because you haven't, it's not only sort of developmentally and cognitively and in so many ways just wrong, but the problem here is that students, despite the fact that they may be able to remember what you told them, have not, by virtue of the curriculum and experience, built any type of framework of understanding, and that's key. What we're talking about is a framework of understanding. So when students are engaging as scientists and engineers in the classroom, they are, the real role of curriculum is to translate the standards into a framework of understanding and supports for effective STEM instruction and mastery level student experiences, such that it produces mastery level student learning outcomes, and the students are well equipped to produce evidence of their learning, whether it's in standardized testing, a job interview, a college application, whatever it is, just talking with somebody on the street. That's what we're talking about here. These are really life skills, okay? So when we come back to this claim evidence reasoning model, the science goes here, okay? It goes in that process, but after, the question, the hypothesis, and so on. And this is what the scientific process and the engineering design process look like, Okay. So you'll see on the left, over here I was talking about the question, the hypothesis, because we're talking about a conclusion. But the actual process itself, you have a little bit of research in there. Research are facts relevant to the question. It informs what we think may be the hypothetical answer to that question. It informs us about what others have done. That's how we use our knowledge. Okay? It forms kind of a research backing. And then our hypothesis, being that hypothetical answer to the question, gives us the point where we begin to summarize our experiment and how we're going to approach that hypothesis through a planned investigation. And so that's where we would then decide on the materials and the procedure, the materials we need and the procedure we would carry out. Then we would actually, maybe diagram that, carry out the plan, gather the data, and then form that evidence-based conclusion as to whether our hypothesis is true or false or inconclusive, using the claim evidence reasoning model that we had talked about here earlier. Okay, that's how it all comes together. So when you think about students as scientists, this is what they're engaging in, the logic of pursuing a question to an evidence-based conclusion. When they're engaging as an engineer, they are engaging in identifying problems and pursuing those problems to evidence-based conclusions as to whether or not the solution that they identified and the specific solution that they diagrammed and built and tested yielded data that justifies refining or replicating. Okay, and so through this, I hope your key takeaway is that the way next generation science standards really work and the way claim evidence reasoning model fits into this, well, claim evidence reasoning coming at the end, right, and that conclusion on either side. This is the claim evidence reasoning where it fits as an 8. But the whole thing we're talking about is high quality instruction that's focused on a higher order thinking, claim, creating, evaluating, and analyzing, and that indeed we are integrating English language arts and math, particularly Common Core, technical subject standards for ELA, communication standards, and so on, nonfiction reading, writing, and on the math side, it's not only data collection and graphing, but it's all of those math practices that are so central to to the disciplines, and that these creative, evaluative, and analytical thinking skills are useful in all disciplines. And so what's only science and engineering really is the experimenting and prototyping itself. It's engaging in the process, learning, discovering and extending our knowledge is what is science only. But in order to do that, it's very hard to do it, to engage as scientists and engineers without language skills, whether they're verbal or written, as well as math. And I'm not saying that to say that ELL students and special ed students don't have a problem with this if the strategies are in place to remove the barriers that are on the student's IEP, or even in the case of intellectually impaired student, to bring them in at a grade level that's appropriate to them as well. I'll leave it at that. I'm going to grab some questions now. I'm sorry I went even longer than I thought, but 3 dimensions here, thinking of that as what is reflected as students carry out the processes, that the curriculum, the professional development materials are what's translating that standard or set of standards, next generation science standards, into effective STEM instruction supports, and that it's the teacher who's really taking those supports, having fidelity to the program, but beyond that, it's their creativity and helping students make those concept to concept, concept to self, concept to world connections, and actually engage appropriately as scientists and engineers. Okay. All right, and like I said, I have all these other examples, but I'm just, with time, I'll get to them if somebody asks a question, but otherwise, I'll flash this information up here for you. Feel free to reach out about anything that I've talked about here. You can reach out to myself by email. I'll reply to you personally. If you want to have a call, I'll be happy to get that set up with you. You can also reach out to Mary Ellen. Her phone number is here, 617-475-3475, extension 2006. And her email is mdelacy@knowatom.com. Mary Ellen was a teacher for 25 years. You can also reach out to Sid Mlaxos. His phone number is just extension 2010 if you can't get Mary Ellen. I mentioned curriculum samples, so it's hard to picture how all of this might look in curriculum. There's a single unit for each grade level, elementary, middle school, early elementary, online. We don't have high school examples yet. We've been doing this for 10 years, actually closer to 12 years now, and we were able to get NGSS aligned really by following the process and really looking at the reports and looking at the recommendations, looking at the standards as just great teaching and learning, and developing those in along the way. And of course, with all the students who have gone through the program, able to iterate and tweak and do so really with the feedback of actual teachers, not only ourselves as teachers, but actual teachers as well in the field with hundreds of thousands of kids. So anyway, you can take a look at that. What you download is only a month's material anyways. If you want to see other material, other months or so on and so forth, just get in contact with somebody. We'll do our best to hook you up. Okay, you can find out about other webinars like this through our blog. You can subscribe to that, knowatom.com/blog, through Facebook, facebook.com/knowatom. Follow us on Twitter, @knowatom. We always like a positive review or a like or a retweet. We love that. The other thing is in terms of resources, we have a whole bunch of resources under the resource section of our website that are free. You're welcome to take a look at that. There are webinars, ebooks, interviews with innovators, actual scientists and engineers. It's one of my things I would say is that if you know scientists and engineers, you know how well everything we've talked about today really fits with what they do. And I don't mean scientist or engineer as the person who goes and sits at a desk all day and works for a big company. I'm talking about somebody who actually invented something, who asked a question and discovered some new knowledge, or who actually solved a problem. Somebody who invented an artificial heart, or a CT scanner, or the internet, or something. I mean, these are not necessarily people you just walk across every day. But if you do, the kind of people who are in the National Academies of Science and Engineering, you will understand exactly why the National Academy of Science and Engineering promoted these standards and the different reports that resulted, and how well aligned they are to innovation itself, and how well served our children will be if they are successful in the years ahead. So with that said, I'm going to go through some of these questions that I may not have answered. I'll do my best very quickly to go through them for you. So give me one moment. Okay, some folks asked about STEAM, different things about the connection of arts and science, technology, engineering, and math. So the connection here is through the exact skills we've been talking about. Okay, the science, technology, engineering, and math is problem solving and answering questions. Math is just a tool for communication. Okay, but the engineering and the science, what we're talking about is problem solving skills. We're talking about higher order thinking skills, creating, evaluating, analyzing. Art is engineered communication. Okay, most people, when they get involved with STEAM, think that it's about students making things pretty or developing an aesthetic. And so by taking that aesthetic approach, unfortunately, the very immediate thing is it lowers art to the level of crafting. And art is engineered communication. And you can see this because if you look historically at artists, famous artists, people who are looked up to in their discipline, those are people who mastered communication, and they did so by creating, evaluating, and analyzing, and being able to turn a message, being able to project a message through a medium like music, like the written word. That's why we call it English language arts. Sculpture, different forms of painting, so on and so forth. You could see this in Pablo Picasso. The guy lived in exile. Yes, did he have a style or an aesthetic? Do some people find it pretty? Sure. Do other people not find it pretty? I bet a lot of people would throw Pablo Picasso's work in the trash if they didn't know it belonged to him, because it, some things look like something a child might draw. But what Pablo Picasso was is a master communicator, and an example of that is Guernica. He was living in exile, and Guernica is this painting he did, and he sent it to the International Art Exhibition while he was living in exile, and it was dark. It was all gray, and it shows women and children and animals, and you can see the animals kind of screeching and the people crying and so on and so forth, and they're kind of as if they're inside a village or inside a house, all alone and suffering. And you think, wow, that's not pretty. It's dark, and so on and so forth. What he was doing was he was communicating the atrocities the fascists had committed at a town in Spain called Guernica, and he was putting it in front of the world to communicate the absurdity of the world's ignorance and lack of action, and its effect on these people in places like Guernica in Spain. And the fascists came back to him, and at least this is how the story is told, and said, what did you do? And he said, I didn't do it, but you did. And so, it shows you just in that exchange how skillful Pablo Picasso was. He took an idea, he evaluated and analyzed the situation, he created a message through painting and projected that out to the world, and he was able to do so skillfully to try and solve a problem of the atrocities that were being created by motivating national players to get involved and to stop it. And there's a great book, I won't go much into this any further, I would recommend the movie. It's called The Rape of Europa, that talks about the role of art in World War II, and specifically in the Nazi takeover of many parts of Europe. And it's just astonishing. It's really astonishing. And when you think about art as engineered communication, and you think about things like propaganda as art, and you think about communication as being for good or for ill, watch that movie, and I think it will change, or at least deepen, and challenge many people's definition of STEAM and what art is. And also the idea that by teaching children the skills we've been talking about in science, technology, engineering, and math, that we are deepening their ability to consume art and also to create it. And I think that that's very relevant even in national politics today, as we see the role that media and messaging and marketing play. It's very, very huge to have these skills. Best ways to introduce the process, I think we already went over this a bit, is basically that, it's something, actually take a look at those first units. I mean, that's actually what our first units do, is they set up the process, the beginnings of the process. And then what we do is we use those processes over and over. We bring engineering into it pretty quickly. And so what we do is we'll teach children one process, and they get really good at using that, and then it maps over to a second process. And then meanwhile, throughout all of the processes, the students are engaging in developing and using the disciplinary core ideas, observing the phenomena and identifying it, and actually engaging in the practices. And so that's where this thoughtful articulation scaffolding come in, where the hands-on materials are so necessary, because a lot of people will go to take something that is hands-on and try and make it an app or make a computer program out of it. And I don't know. Would you rather talk to an app or to a person when you do something? Let's say that you're trying to get tech support for something. Would you rather talk to a person or to a computer? I don't know. I think most people would rather talk to a person, because there are certain things that computers are not able to solve if it falls outside the realm of something very specific that's been identified previously. Humans, however, can deal with ambiguity and help find solutions to things that are not necessarily known. Well, when you take something that's hands-on in a phenomena like anything, I mean, you could take the old baking soda and vinegar mixing, okay? You can make that into a demonstration that's on an app and in a computer, but it's not the same. It's not something that students, especially in this, it becomes an even bigger issue the younger that students are, because the computer program can only do what it was told to do. And there is infinite things that are happening here, and to have something that's kinesthetic and hands-on, it makes a real impact. So the reason I bring that up is that it's really important that students are able to engage in the practices, I believe anyhow, engage in the practices hands-on, and solving real problems hands-on, and being able to observe that phenomenon firsthand and not how somebody interpreted it and then put it into some computer program, which in and of itself, as a different medium, has all its challenges. So last question or two. Let's see here. Folks asked about units in introducing the process. We introduce process every single year. So pick a grade level. All of our curriculum is grade specific. And so that's important. Something's not aligned if it's not grade specific by its design. Now that's different than having grade specific standards, okay? Grade specific standards does not mean that a standard is taught only in that grade level. It needs to be taught in adjacent grade levels, introduced, mastered, reinforced. That's what quality curriculum does, right? Bring student to mastery. That's how you do it. So when you see something that's like, for grade 3 to 5, you could do this with your 8th grader. You can do this elementary engineering thing with your 3rd grader. Not really. It puts it on you to somehow change that, because 3rd graders are very different than 5th graders and very different than 8th graders. So take a look at any one of those big units. Other folks have asked where they can get units. Just go to KnowAtom.com. At the very top of the screen, you'll see STEM curriculum. Scroll down, you'll see different grade levels. Just click one. You can download curriculum, take a look at the unit, the reader. If you are from Massachusetts, we're I think the only company that has a Massachusetts aligned to their new standards curriculum. So take a look. There's a link in there for that too. I recommend using Chrome with our website. Sometimes people use Firefox or have different browser settings that are a little bit wonky, so on and so forth. If you have a district that is stuck, if you need help, please reach out to us. We may not be able to help you, but we're here to help, and we can try to point you in the right direction. If you're in a curriculum review process and you are trying to find next generation aligned resources, if you want to get your district up and running quickly, try to have everybody on the same page so that your PLCs can focus not on who found what resource where, but instead on effective instruction and meeting student needs pedagogically, and really how one student's reacting to a challenge versus another, and trying to really think as a team around strategizing and meeting those student needs. That's something we can help with. That's what our resources do. They translate, when you look at, and I'll show you here really quick, our resources take care of turning those standards into curriculum and an experience, because it fits right in here, and then it supports that teacher with the background, the lessons, the units, the assessments, and everything, the answer keys and so on, chronologically, scope and sequence, the whole deal, so that student learning, high quality student learning, can take place and there's evidence of that learning. So that's what we do. And some folks have asked about scaffolds. This is kind of what it looks like here. It's not kind of, it is, it just depends what state you're from. So you can see grade 1, there's 9 units, it's a monthly theme, same grade 2 and so on. And it's integrated across all these different disciplines, because again, remember, we are bringing purpose into science and engineering. We're asking questions and solving problems with a purpose, and we meaning students. We students are doing that, and so the curriculum is helping us discover connections. And so you see through grade 5, through grade 8, kindergarten is currently in development, but it's only being released to select districts right now. Same thing here. Okay, so with that said, I hope that you found this helpful, and I won't go through all the resources. here for you. We do have other webinars that will do that. I can show you a little bit of data on the way out the door. So you can see in some examples, here's an elementary example, and this one here, I'm picking on Massachusetts again. This is an urban school, 72% low income, 65% free lunch, 75% high needs, 35% English language learner. And over the course of 2.5 years, they added 51 points to their, or 52 points, to their advanced and proficient scoring students. The state average is only 50%. So quite a feat. Here's another, in the same state example, they added about 20 odd points to their, right out of the gate, to their advanced and proficient scoring students. And you can see the effect that it has on that needs improvement and warnings low here. And this is that higher need urban school. This is the more suburban school. Why do you get increases, or why do you get these kind of bumps in the road? Well, teachers matter, administrators matter. Change in teacher, change in administrator. Teacher was here, administrator over here. That's how it is. Lack of professional development, new teachers, no professional development. Those things make a difference. We actually, in Massachusetts, as just an example, we have, I think, 2 out of the 3 or 3 out of the top 5 highest performing elementary schools. I don't know about middle schools, but elementary schools in the state. So like 92% proficient or so. Like here's an example of one that's pretty close. I think this might be the highest performing district. This is 89% advanced and proficient. So it is what it is. This is a really deep inner city school, say 1,200 kids or so. Tested at 8th grade, and you can see over the course of 2.5 years here, they added 24 points to their advanced and proficient. Look at their warning failing. So in Massachusetts, if you're from a different state, this is below basic level students. It's typically what it's called. They went from 54% to 27%, basically cut it in half. So and that's in a school with 64% ELLs, 95% low income, 87% free lunch, 97% high needs, and you can see the shift right here. It's not our data. This is all state-level standardized testing data that I've been showing you. So it makes a big difference. Thinking matters. The way that we engage students in the classroom matters. And, of course, that curriculum and resource material matters. So with all that said, I apologize to have kept everybody so long. I'm happy that everybody was able to join. And if you were joining late and perhaps had the time wrong, if you're not in the Eastern time zone, if you were in the Central or even Pacific time zone, it'll be about an hour and 45 minutes, a full recording of this entire webinar will be available for you online. Keep an eye on your email, junk box spam filter. If you don't get that link, let's say within the next 24 hours, you can either revisit the page that you did to sign up and just basically resubmit your information, and you will be able to access that video instantly, or just email somebody that's on your screen here. You can email myself. I'm CEO here now at KnowAtom, Francis Vigent, or you can email Mary Ellen DeLacy, mdelacy@knowatom.com. Give her a call. Again, I'm sorry I wasn't able to get to all the questions, but feel free to give a call. I hope you enjoyed the session, and I really wish you great luck implementing these new next generation science standards, and I hope that you see how claim evidence reasoning fits with this next generation model of instruction in terms of those evidence-based conclusions. Thanks a lot, and have a great day.